Let's do a quick review for the vacancy-mediated self-diffusion in ionic solid materials. And the type for vacancy formation will be the Ch4 defect. So as we mentioned before, if there were Ch4 defect formed inside potassium chloride ionic solid materials, then you can formulate these reactions before there's no Ch4 defect, then we form a pair of uh, positive and negative ions, or positive and negative vacancies, a pair of potassium vacancy at potassium side with a negative charge, and also the vacancy at chloride side with positive charge. So will be the pair of vacancy. So as we mentioned, so uh, we have chance to know the vacancy fractions for potassium and chloride due to we have Vk equals to VCl, and this times length equals exponential negative Ch4 defect formation gives free energy. And in the meantime, you know Vk equals to VCl. So here we can get the Vk and also VCl equals to exponential negative Ch4 defect formation gives free energy divided by 2kT. Now we know this fraction term. This actually is xvk and xvcl, right? So as long as you times the dV times F, you got the diffusivity for potassium ion and also chloride ions. So we directly, so what's the dV? Based on the vacancy mediated, uh, the vacancy mediated mechanism you derive before, we know that self-diffusivity equals to this, show like this. Fa squared mu exponential, and we have two terms, included the vacancy formation and also vacancy migration. So actually you got this results in, as we mentioned in PPT slide here. So we just copy this results. Okay, this results back to here. But as you know that the structure for these ions actually is double FCC structure, not directly FCC. So due to here, we need to put a G for diffusivity. So we also have diffusivity of potassium ion will be XVK diffusivity for potassium ion move in vacancy at potassium side and times F, and G is due to here actually is a double FCC structures. So G actually is geometric factor, which is highly related with crystal structures. Okay, so we'll be ranging from 1 to 2. And so here, VK actually is here, so you just have a Ch4 defect formation gives free energy. Then I separate them in enthalpy term and entropy term. So this is the gives formation gives free energy, XVK. And diffusivity, I just put here the rest of it. So diffusivity is the green one, is diffusivity. So I copy them. Actually, it's a migration energy. Migration gives free energy, included the cation jump in vacancy, cation jump in vacancy term, and put also the G here. Okay. And the same for chloride ion. And ion here is XVCl diffusivity for chloride. Big chloride jump in vacancy at chloride side times F. So the same, this is a Gibbs free, give a Ch4 defect gives free and Ch4 defect gives free energy and migration, green one migration energy. But here is an ion jump in vacancy at chloride side, and also put a G. So F has been included here, so I did not include the extra F here. So this is the diffusivity for the energy, diffusion energy for both ions actually is the temperature dependent included. The Schottky defect formation enthalpy divided by 2 plus the migration enthalpy. So this is um, um, this is the results demonstrate that the facility for potassium ion or chloride ions, and also we have a Schottky defect form inside our materials. But how about, as we mentioned that, um, in order to tune the diffusivity, as it turns out, as long as you change the vacancy at potassium side or vacancy at chloride side, you can easily tune the diffusivity. So for potassium, we use this as an example here. As long as I do something to change the VK, increase the VK, then diffusivity will be increased. So what can I do here? So some people will use a dopant here. So what's the fourth story? Extrinsic ionic solid means that I have a dope in this ionic solid material. So I call it as extrinsic. And the one is intrinsic, no dopant, no purity. So extrinsic ionic solid materials also we have we form a pair of vacancy due to the Schottky defect. And we doped calcium with 2 positive charge in potassium chloride is ionic solid materials. So calcium with 2 positive charge. So the easy way here we ended the calcium chloride into a dope into potassium chloride. So I will write down this is a dopant and dope ended in potassium chloride. So under these situations, the calcium ions will occupy the vacancy at the potassium side. But due to this is 2 positive charge and this is just 1 negative charge. So if calcium move or occupy the vacancy at potassium side, then that will carry extra positive charge. We have 2 positive minus 1, so we have 1 positive here. And the rest of chloride will locate or occupy at chloride side here, so with neutron. But I will have extra vacancy at potassium side here. Due to what? Due to you have 2 chloride, right? So usually 2 chloride vacancy can allow you to sit or to tolerance 2 chloride. So that means you also need to have 2 potassium because they always pairs in pairs, right? So one be occupied by calcium, the other you will left 1 vacancy at potassium side. 所以这里的话很重要是说，我现在要掺杂叫 extrinsic。我掺杂，那这时候我掺杂是氯化钙，钙是2价的。那这时候把氯化钙掺杂到这个氯化钾里面的时候，化学反应是会是氯化钙，然后这个会是我的 host，我的 ion 就是氯化钾。那这个时候钙离子它有钙离子跟氯离子嘛？那钙离子的话，它就会因为它是正电，那它就会想要占据负电的 vacancy，那这时候它就会站在这里。钙站在钾的 vacancy，那它有二正，然后它只有1个负，所以它这边会多1个正，2减1就会是1个正。然后氯的话，它的氯就会站在原来氯的 vacancy，它就是氯离开的这个 vacancy，然后就氯站在氯，所以是 neutron 的。但这里有2个氯，如果你有1个钙，就会有2个氯。所以从这里就可以知道，如果要容纳一个氯化钙的倍率的话，这边要有2个氯，所以它也会，因为它是总是一对生成，所以它也会有2个钾。但1个钾被钙给占据了，那它就会留下1个钾。So one calcium occupy 1 vacancy at potassium side and leave 1 vacancy at potassium side. This is how it works. So if you still don't have any idea, I have drawn a simple cartoon to represent it. We form some pairs of Schottky defect. And here we have 1, 2, 3, 3 pairs of Schottky defect, and we dope the calcium chloride into potassium chloride. So we have a calcium. Calcium will occupy at one vacancy at potassium side, but now is with one positive charge. And the chloride will occupy vacancy at chloride side, and we have one calcium chloride. But at this situation, you see that consider to electrical neutrality, we have extra vacancy at potassium side. This one positive, one negative, so it can be considered as electrical neutrality. So we have one more vacancy at the potassium side. Here we have one negative charge. It implies that if you dope more calcium chloride, you will get more vacancy at potassium side, which also imply that vacancy at potassium side will increase as long as you dope more here, and the diffusivity for potassium side will increase as well. 从刚刚那张图就可以发觉说，如果我有3对的Ch4-2 defect 缝了，对不对？然后接着我 dope 一次给大家看，就可以看到说，哎，我 dope 更多的氯化钙，这个时候单独的，它们两个算一对一种，就电中性了，所以多的这个 VK 就会，如果 dope 越多这个，那 VK prime 就会越多，所以 VK prime 越多的话，我只要多了一个钙，就会多一个这个，应该这样讲会比较精准。所以就是说，在这个情况下，VK prime 的浓度就会增加了。那这个时候 VK prime 的浓度增加，我 diffusivity for potassium 就会增加，也会改变，所以 diffusivity 就会增加。But how it changes, it will be very important. So we want to have to estimate. So based on concentration of charge defect, all positive charge will equals to all negative charge. So calcium at potassium side with one positive charge, less concentration or less fraction, plus vacancy at chloride side will be equals to vacancy at potassium side with one negative charge. So here we want to know, in order to know the decay, we need to know the VK, right? Under how the VK changes. As long as we know the VK, we can estimate the decay. So here I want to formulate the VK. It's quite important. So here, as we know that a pair is a Ch4 defect formation, right? So you use this times this, you got the Ch4 defect formation gives free energy here. And in the meantime, there's no dopant, right? It belongs to intrinsic materials. So you will get VK prime square pure. This is similar to before dope. When you times the major carrier electron and also the host, then you will equals to Ni square. So this is pure, which means that there's no dopant. And based on here, so you will have like, as we mentioned before, when you learn the semiconductors, you know when I times the concentration for electrons and holes, then I will get Ni square. The Ni actually is before doped. Okay, so as we mentioned before, under thermal equilibrium conditions, intrinsic semiconductors, the concentrations for electrons will equals to holes. So you can get N equals to P and equals to Ni. This is for non-dopant. But if you have a dopant, lightly dopant, then you will get N times P equals to Ni squared. Then N here will be also the electron concentration in the semiconductor, and the P here will be, some people will write down N0 and P0. So P is the holes concentrations in the semiconductors. And Ni the same, less no dopant, but after lightly dopant, you will get the new concentration for electrons and also for holes. So you have this idea. So we use this concept to here. After dopant, Vk times Vcl will be Ni squared. And based on here, you know that in order to know the Vk, right? My purpose is want to know the VK prime, not the VK. This is no dopant, right? So I need to, but here I have two unknown parameters. So I have one equation here. So in order to, I can substitute this in terms of VK if it's possible. So here I use this to minus this one to substitute this term. So next, I will use this equation to get the VK. Show like this. This will be a squared minus, or x squared minus ax minus b squared. So I can get this one. So the vk can be shown here. So this is a little bit complicated terms, but if you take a look carefully, we need to figure out this term and this term, which one is larger. Vk in pure ionic, no dopant, no intrinsic ionic material, Vk, the concentration Vk is higher, much higher or much lower than the dopant, then we will know the Vk, right? So the same idea here, if Vk prime in intrinsic ionic solid material is much larger than this one, this is much larger than this one, I can ignore this and square root of just this term. So I will get Vk prime equals to Vk intrinsic ionic solid materials. So due to I know Vk prime equals to here, so I can substitute this term. So this will be Schottky defect formation energy, xvk will be Schottky defect formation energy divided by 2kT. And dV will be the term we just learned. Copy here. I did not like, this is good for energy. I did not separate them in enthalpy and entropy term. So this is Vk in intrinsic. So this actually is this one. But however, if the Vk prime in intrinsic ionic solid materials, this is much larger, right? How about the dopant? We try to increase the dopant concentration to allow the dopant is much higher than the Vk prime in intrinsic ionic solid material, which means there's no any dopants. Then Vk equals to here, so I can directly use the dopant concentration to substitute this term, and this copy and also F. So it turns out what? It turns out depending on the concentration of dopant, you probably will have two different Vk, and different Vk will contribute different diffusivity of potassium. So based on here, we know that if you try to plot the log D diffusivity for potassium ion versus 1 over T, then log this equations, then you will have a slope for temperature dependent term, right? So I will convert them in enthalpy. So I will have this and this plus this one. So this slope will be larger, higher than this one, because this is a dopant concentration, nothing related with temperature. So I only have this term. So when I try to draw this extrinsic dopant control part, will be a lower slope. Show like this. Only have a migration enthalpy, right? So this result actually tell us what? If at higher temperature, lower temperature probably will be the dopant control. like room temperature. In some cases, we will dopant control. But in higher temperature, 1 over T higher, I have higher, so 1 over T will be smaller, will be intrinsic that control. Okay, so that will be have lower temperature, increase to higher temperature. So depending on your targeting temperature, probably in some case, if you're interested, temperature will be range here to here, then you try to plot the log D diffusivity versus 1 over T, then you only got one slope, which only means that one diffusion mechanism dominate. But if your interest in temperature is at lower temperature, so you at within this region, when you measure the decay at different temperature, then you only get one slope, also which tell you that dopant control. But if the case you just randomly pick the temperature and you get this like this curve showing black, this obviously tell you that within this temperature region, two mechanisms dominate with in corresponding activation energy. At lower will be dopant control, and at higher temperature will be intrinsic control. So after fitting, you will know what's enthalpy for Ch4 defect formation enthalpy and vacancy migration enthalpy. So for example, like if you got this results showing black line, then after fitting, you can from this slope, you can get the vacancy migration enthalpy. And based on from this slope, you will get this times this one. And here I already know the value here, so I will know the vacancy formation enthalpy in this case. Okay. So if the question asks you, is that possible to measure the vacancy migration enthalpy and Ch4 defect formation energy? How can you design an experimental to know both of this? Then you can have this, like you can use this trick. 所以从这里他就可以知道说，如果我的钾离子的vacancy 的 fraction，钾离子的 vacancy 的量改变的话，diffusivity 的钾的 diffusivity 就会改变。如果这个增加，那它就会增加。所以只要会动到 VK 的钾的 vacancy 的浓度占比的话，那 DK 就会改变。所以 dopant 是一个很明显可以调整 DK 就 VK，然后最后调整 DK 的方法。那如果我们刚刚说的就是有这两个机制嘛，那你把图画出来之后，你就可以知道说，在高温的时候其实是 intrinsic 主导 DK，那在低温的时候，如果你有 dopant 的话，就会是 dopant control。然后所以，但如果你不知道，你的到底有几个 control，最简单的方式就是在你有兴趣的温度区间就 plot 这个，然后看它是一条线还是两条线。如果它是一条线的话，那就是一个就是其中就只有一个机制 control。那如果它是曲线，那就会 fit 成两个 slope，那就表示说在你的扩散里面有两个 activation energy barrier，那就表示有两个机制，好不好？所以这个是 for your reference. So this is extrinsic, which means that dopant. When you add the dopant, then they will change the VK, then further change the diffusivity of potassium. Okay, so this is a slide just for your reference because some people have no idea the vacancy fractions. So I just give you some value, just hope you can have some concept here, idea here. Potassium chloride, Ch4 defect formation energy to form a pair vacancy in this case will be ranging from 144 eV. So in this case, potassium chloride, the Ch4 defect formation enthalpy is around 2 eV. And at 1000 K is around 700 degrees C. Under this situation, you just put all the parameter inside. You know the fraction, vacancy fraction will be in the order to 10 to negative 11. But if you have a dopant, usually dopant concentration will range from 1 to 10%. And under this situation, the fraction for dopant would be much higher than the vacancy fraction. So just for your reference, this is much larger. So as long as you have a dopant will be dominant or contribute a lot in the diffusivity of potassium. So this is the case we want to address with. Then I will want to talk the last part, which will be the unfamiliar one, which we call a non-stoichiometry effect in ionic solid materials. What's a non-stoichiometry effect? Instead of like explain what it is, I just give you an example and hope you have some idea to know how to discover or how to know your case your material have a non-stoichiometry or not. So what we have here is we have a diffusion. The diffusion of FeO ionic solids is through vacancy mechanism. So vacancy, and this is ionic solid material. So you need to think about either through Ch4-2 or Frankel defect to form a vacancy, a pale vacancy. And now FeO ionic solid dope with no amount of TiO2. So we dope TiO2 into iron oxide, FeO. And after we measure the diffusivity for these iron ions from at T1, T2 to T3, and we visualize there are three slopes observed in this plot, which plot is log D versus 1 over T. And based on here, you can write it down actually three slope, which means that there's during T1 to during T1 to T3 involve three diffusion mechanisms. So that's why we have three slope. So how many diffusion mechanisms of iron involved in the temperature is three. Why? Because they have three energy barrier activation energy. But can you establish the diffusion kinetics model involved, which means that these three diffusion, what are these three diffusion mechanisms? And please derive the diffusivity in terms of VFE as function of temperature. So this idea actually is three, right? So as we mentioned in prior slide, lower temperature will be dopant control, higher temperature will be intrinsic. So we have one more, right? So the one we want to address will be the non-stoichiometry effect. So we first to formulate the DFE in terms of VFE, vacancy at iron side, at high temperature here, intrinsic Ch4 defect formation energy, and lower temperature will be dopant control. So here we assume this happens, we have a Ch4 defect formation in these materials. We assume that. So Ch4, so as we mentioned, and this is dopant, so as you know, we always form a pair of vacancy for VFE and VO, right? So VFE and VO. And this times this, we got the equals to exponential Ch4 defect formation and gives free energy. And this equals to this. So VFE will be right down to put here. So I got here. So I know this, just substitute here so I can get a D. This substitute here and dV, I assume is FCC. I'm not sure whether they tell you. Okay, it turns out it forgot to give me this information. So we assume is double FCC structures. So I have GA square mu, the rest of put everything back. And for lower dopant part, the dopant at low temperature dopant. So as we mentioned, low dopant control. So would be I dope the TiO2, and Ti is with four positive charge. Occupy at vacancy only have two negative charges. So I have two extra two positive charge, and all occupy at all, and I will have extra vacancy at iron side to check two positive, two negative reach the electrical neutrality. So the dopant control, so this will be equals to dopant. So substitute this dopant and copy this term times F. Perfect. This is dopant control and GF. So if you forget the one we just addressed with, so dopant control, which means that will be go this way, is extrinsic. Okay. Okay. So back to here. So, but still, as we mentioned, based on the questions, we do have three slopes, right? But here we just explain at higher intrinsic dominant, lower temperature, dopant control. So we still have one more showing. Blue is non-stoichiometry effect. So what is this non-stoichiometry effect? Before we move to here, you know that how to know if this non-stoichiometry effect happen in your ionic solid materials. When you measure the diffusivity of iron, your interest in iron versus 1 over T, then you visualize and close temperature, you visualize there's a three slope, and the middle one would be non-stoichiometry dominant. So in order to check whether you have, so this three temperature, you need to have a large temperature window. Okay. Okay, so that's explain what is a non-stoichiometry effect, what this means. Based on the questions, actually we have a matrix we have is FeO with two positive charge of the iron, two positive charge. But non-stoichiometry effect, which means that inside my material, not only my iron with two positive charge, and I also have some iron with three positive charge. Not all the iron have the same positive charge. That's what you will call it as non-stoichiometry effect. 就是在你的材料里面，我的铁离子在这里面看起来是只有二价，对不对？但当我的系统里面有二价铁跟三价铁，这因为在这个 case 里面我们没有一价铁嘛，不会有一价铁存在，所以就是有二价跟三价的时候，就会在这个系统里面不单纯只有二价，还有三价的时候，它就是 non-stoichiometry effect 发生的时候。So in order to interpret why some iron was to positive charge, now it's converted to three positive charge. So I have a simplified cartoon to represent FeO. We have O here and iron around it. Then what happened here is to convert it with three positive charge, which means that the iron will lose the electrons. It lose electron, which means somebody take these electrons. And the only one who can take that would be the oxygen, neutral oxygen. So under we have the oxygen in our environment, then this oxygen will take the electrons to become two positive charge. Under these situations, I will visualize that this will be, because I lose, this will put here, right? So, and this, as long as we have oxygen with two positive charge, and this iron will move to here. Because the iron moved to here, so that will leave a vacancy at iron side. Have a vacancy at iron side, and here you will have three positive charge of iron. So in order to write them down, so you will have iron with two positive charge, then lose the electrons. These electrons is due to the iron moved to here and left the vacancy. So you sum this together, so you can write this and this to this and delete the two electrons part, and also can further rewritten as iron at iron site, oxygen doesn't matter, but iron at iron site now converted to three positive charge, but now actually it was two, right? But now have extra, so have a one positive charge. And two negative charge oxygen at oxygen side, but here it will left a vacancy at iron side. So check actually to reach electrical neutrality, this is two positive charge and two negative charge. So once you have these equations, then you can formulate the K equilibrium. This times this to times this is neutron, so this to 2 it holds to 2 and vacancy and divided by here. So the partial pressure of oxygen and the order is 1 divided by 2. This will be this equation gives free energy. And as we know that as long as you have one hole, if one, you will have two parameters. So I'm more interested at VFE, right? So I need to convert this or link this in terms of VFE, vacancy at iron side. So I will have VFE. So if you have one hole, if you have one V, then you will get two moles of hole, right? So this is one V. Then you will have two moles of hole, so one V. So you got the two here. So I can substitute this in terms of VFE. So I will put a 2 VFE squared and will be 2/3. So I will get the VFE show here. And as we know that substitute here and times dV, then finally I can get the diffusivity for iron will be turned, this is VFE dVF. And for the slope, temperature, I have this term and plus this term. This is the this term, and this is this term. So this is demonstrate that there's non-stoichiometry effect in ionic solid materials. So any questions? 所以在这里的话，重点应该在于说，你要一开始判断非剂量比的时候，因为正二的话，它就只能不会变正一正三嘛。那正三的话，它就是失去个电子。那记得失去电子要有人拿。那在这 case 里面的话，它不会是氧离子，它不可能再拿一个变负三，所以它一定是外面的氧气有机会变二负。所以就是氧气得到电子之后就变二负，然后这两个式子加在一起，那电子会散掉，变这个加这个，变这个加这个。然后这个的话，要把它写成就是离子的，刚刚就是我们整个式子的比较习惯的状态，就会是铁还是在二价，所以铁在铁的位置是 neutron，然后氧气，但这个时候铁的确还是在铁的位置上，但因为它这个时候已经变成正的。因为它的电子跑掉被抢，它就是它把电子给了就是氧，所以他们两个就是它在它三价的铁站在二价的位置，所以会多一个，然后接着就会是铁的 vacancy。那这边的话可以 double check 一下，这边会是中性，是二正跟二负。Okay, in order to make sure whether you understand this or not, actually you can take a look on the lecture, the TS notes. Let me take a look here. We have the other example here, show here. This will be this is CaO doped ZrO2. So ZrO2 is 4 positive. This is our matrix. We ended the CaO into ZrO2. So also we found, and we talking about also the vacancy mechanism, and ZrO2 actually is FCC package, and also Ch4 defect dominate the diffusion at high temperature, and plot the log the diffusibility of oxygen versus 1 over T and so on. So as long as we want you to draw 1 over T in this case, which means that you need to make sure, as we mentioned, doing the temperature range, higher temperature or due to intrinsic, lower temperature will be contribute from the dopant. So, and don't forget the matrix is the ZrO2. So I use a cartoon to have you simplify ZrO2. We have a 4 positive and oxygen. So this is one pair, 4 negative, 4 positive. Pair is neutrality, this neutrality, neutrality, neutrality. It turns out makes sense. So here at higher temperature, would be Ch4 defect. So we form the Ch4, right? So we have ZrO2. So Zi is 4 positive. VO will be 2 Zi is 4 positive. So vacancy will be 4 negative. And oxygen will be 2 positive. So I have 2 here. And this times this square because of this elementary reaction, so this is to older. So be Ch4 defect gives free energy. And as we know that as long as you have one VO, oh sorry, one moles of vacancy at ZR, you will have 2 more also of VO, right? So will be 1 times 2 equals to 2. So, and here the equation of always is this is not zero, it's O. So everything I need to replace as VO. So I substitute VZR as 1 divided by 2 VO, right? So I can get this result. VO turn here. So substitute this VO and times the migration turn GA square F mu. So this is a DO, the possibility of oxygen. And for the lower temperature will be dopant dominate. This will be I dope CaO. Ca is 2 positive charge, and so Zr vacancy at Zr actually is 4 negative. So I still have 2 negative here. And that will to reach the vacancy or to reach neutrality, so 2 negative, so I will have 2 positive vacancy of oxygen. So vacancy at oxygen will be equals to the dopant because one more. So I substitute this, and the rest of part actually is a migration turn. And the most difficult part, would be some people probably is not have that. So I did draw like here. If you double the calcium at vacancy at ZR side, actually this I think this draw have some questions, so ignore this one. Okay, so because actually the calcium should occupy the ZR side, right? So V vacancy at ZR for negative charge. So I should have a calcium here. So let's draw actually is wrong. Okay, so let's draw this draw actually is not that right. So ignore this draw. 噔噔，这是画错的，就是我的 CA 应该要站在这个，因为我有个 Z 啊， 因为我的 ZR 跑掉了嘛，所以我的 CA 应该要放在这里。然后 CA 是二正，然后离开的 ZR 是 V，vacancy 的话是四负，然后加二正还会二负，所以它这个画的不太好，它应该要画这边，好不好？那不要看那个画图的，我们就 OK OK。So then we move to oxygen deficient knob dominate. 那 in this case, ZR, actually we have for positive charge. So actually we don't have for a 5 positive charge of ZR, right? So must be have, if it have a non-stoichiometry, geometry, must have a 3 positive charge. So you can have a look. I have a draw. 3 positive charge of ZR. Okay. So under what kind of condition you will visualize the 3 positive of charge? So which means that um, the 4 positive charge become 3 positive charge, which means that it receives the electron. And which may also imply that somebody given the zinc electron. So who can give zinc the electrons will be oxygen with 2 positive charge. So that's why we will write this down. So oxygen ion at oxygen side with neutron, but actually it have a 2 positive charge. So it will release the electrons to back to oxygen molecular. So we have 1 oxygen, so it will be 1 divided by 2 oxygen and have 2 electrons. It give two electrons to zinc. So here I will left the vacancy. This is 2 negative, so I have 2 positive vacancy at oxygen side. So as we mentioned, this will be equation, so I can write it down. K equilibrium will be this partial pressure and the order here, this square, this times this will be this equation gives free energy, negative gives energy divided by KT. And as we mentioned, if you have 1 vacancy at oxygen side, you will get 2 moles of electron. So the relationship will be 1 here, we got 2. So I substitute this term in terms of VO, substitute back. So here I have 4 VO squared, 4 VO to 3. So, and take the VO, so I will get this result. And this substitute back to here, so I can get the D0. Because this is a VO, then XV here, substitute this term. And the rest of part will be migration. Term, A square F mu. This will be migration, dV. And G, put G here because it's ionic materials. It's double FCC. This is G, geometry factor. Okay, so this is for your reference. So I'm going to move back here. Give you a quick summary for diffusion mechanism. From first from the first part, we based on the random walk, we derive the diffusivity can be written expressed like as gamma. Each jump distance, mean square each jump distance divided by 6 times f. This is 3-dimensional case. For interstitial or vacancy, f equals to 1. But for the host atom, they diffuse through vacancy or interstitial side, self-interstitial side, then will be xv dvf or xi dif. And you also need to remember how we design an experiment to determine the vacancy formation and migration energy. For the last part, actually, we talk about the vacancy-mediated solute diffusion. And that involve, due to we have a host, we have a substitutional dopant at lattice point or substitutional site. Then that will cause 3 different types of atomic jumping frequency. We have 3 different gamma prime. And you need to, in order to know the diffusivity for this solute, you need to consider which one is a rate determining jumping process. And at that case, actually, we find the highest one, gamma prime, won't be the limited step, usually will be the second one. Okay, and the last part is diffusion in ionic solid materials and through vacancy mediated diffusion. So we have two vacancy formation mechanism. Is one is a Schottky and the other one is Finkel. And in order to formulate this equation, this type of equations or this type of equations, please remember you need to have charge defect equations. You write down the charge defect equations, and you need to make sure diffusion mechanism is the Schottky or Frankel defect. And do we have a dopant or just intrinsic? And do we have non-stoichiometry or OR stoichiometry? And don't forget the purpose, as long as you need to know the XV, the fraction of a vacancy, then you can know the diffusivity. Okay, and just a quick reminder, vacancy one will be also use the XV-DVF for interstitial, self-interstitial defect. Involved, we're talking about the Frankel defect, also would be XIDIF. Okay. So we just ended the lecture 4 and hope you can have a review for this one, especially the non-stoichiometry part.